Okay, this is my first attempt to record a video on PowerPoint. So we're going to get this in one take and it's going to be great. There will be times where it'll stop you and tell you to answer questions about what's going on. So make sure you complete all those questions to show that you truly watched the video and take notes as you go. The topic is going to be limits, which is our new unit in pre-calculus. It's our first kind of our first time diving into calculus. So before we can do this, our objectives are to review average rate of change, because limits applied to average rate of change is a key concept in calculus, and average rate of change is a way to approximate a different key calculus concept. So in order to jump into this, also the reason that we're introducing the topic limits is because it's an entire unit in AP Calc classes or Calc 1 classes, and the reason that it's an entire unit is because it's the foundation of multiple key concepts in calculus. Okay, so we are going to start with finding the average rate of change of this function, f of x equals x squared minus 2x, from x equals 1 to x equals 3. You may or may not have a memory of how to do this. I'm just going to jump in and tell you that we need to find the change in y over the change in x, which you might have remembered as being like y2 minus y1 over x2 minus x1. Another way of saying that is f of 3 minus f of 1, because those are our y values. And then obviously our x values are 3 and 1. So we have to figure out what our y values are by plugging into our function. F of 3 is equal to 3. If you need to pause the video to write this down and double check the math, go ahead and do that. We're plugging in 3 for the x values. We're plugging in 1 for the x values. So we have our y values as being 3 and negative 1. So then our calculation is 3 minus negative 1 divided by 3 minus 1, which gives us an average rate of change of 4 divided by 2, which simplifies to 2. So that's all the average rate of change review we're going to do. There's a million examples of this if you look it up online, just where you have a function and you need to find the change in y over the change in x, okay? Now we are going to connect this to limits. So make sure you have a calculator to work with. And we're going to start by taking this function x squared plus 7, and we're going to plug in 1.9, 1.99, 2, 2.1, and 2.01. This is my first time that I'm going to ask you to actually type in your answers, so the video will stop and allow you to import answers into Google Classroom. So do this on a calculator first, input answers, and then the video will continue. And here's what you should have been getting, 10.61 all the way down to 11.0401. And what we just did here is we took a limit as x approached 2 for this function x squared plus 7. So you should pause the video and take a second to write down this text on the right side of the screen. We have our new notation, and this notation is used to show that we're going to take our input and allow it to approach a certain value, and then the limit itself is going to tell us what happens to the output. In this case, it's 11. So pause the video and write this down. And this seems kind of silly and pointless because we know that this function is going to approach 11 as x approaches 2, because that's what the function is equal to at x equals 2. So of course, on the graph, if we get closer to 2, then the output's going to get closer to 11, right? So this is not very useful to take a limit when we already know what's happening in this quadratic function as x approaches 2, okay? So before we jump into useful limits, here's a couple of other examples of limits that are not useful. As x approaches 5, this function is going to approach 21, 5 squared minus 4. As x approaches 2 in the bottom function, that y value is going to approach 7 because 2 cubed minus 1 is 7. So it's not useful to plug in 4.999 or 5.001 or 1.999 or 2.001, because that's not going to give us any different information than if we just plug in x equals 5 or x equals 2, okay? Where limits end up being useful is in functions like this. You may remember from Unit 2 that there's a special key feature happening here at x equals 2, and that is a hole. And how we covered finding the y value of holes in the rational functions unit is you cancel those x minus 2 factors and then plug in 2 to whatever is left over. So we do 2 minus 4 is negative 2, okay? This is giving us an example where limits actually might be useful, because we can't straight up plug in 2 to this function. If we graph it and we go over to where x equals 2, there's going to be an undefined value and it's going to give us a hole, right? But what we are allowed to plug in is numbers like 1.99 or 2.01. And we can see with both of those inputs, the output is really close to -2. And that does end up being the y value of our hole. So limits allow us to figure out what's happening in a function, even if the y value is undefined, because we can just plug in x values that are really close to where that undefined point happens. So here's another example where we are not allowed to just straight up plug in x equals 3, but we could plug in like 2.9999 or 3.00001, right? We also have the benefit, though, of having our method for finding y values of holes from the rational functions unit. There must be a way to cancel an x minus 3 here. So if we factor that top as x minus 3 times x plus 3, now we can cancel the x minus 3's, which just leaves us with x plus 3 over x plus 4. Now we're able to figure out where the hole is by plugging in 3, and we get 6/7. Just as a quick side note, I did make this particular example around like 7 or 8 years ago, so it is a coincidence that this answer ends up being 6/7. But anyway, moving on. That is what our limit would be equal to. If we plugged in numbers really close to 3, like 2.999, our output would be a decimal that is really close to the decimal of 6/7. Okay, so still there's no context for our holes. They're not really like doing anything interesting for us other than just existing, okay? Where there are holes that do have context is when it comes to calculating the slope of curves, okay? So your next task that the video is gonna pause and have you do is find the average rate of change of square root x on these different x intervals a through d. You should use the example. So for part A, we plugged in square root 4 minus square root 3.5 over 4 minus 3.5. Plug that into a calculator, make sure you're getting 0.258, and then repeat that process for 3.9 to 4, 24.5 to 25, and 24.9 to 25. For the other function, the average rate of change is going to be calculated differently because it is x squared. So make sure that you're plugging into the function x squared when you do your average rate of change calculations. Do your best on this. Once you advance the video, it'll show you the answers to all 8 average rate of change calculations you're supposed to be doing. Here are our answers, 0.258, 0.252, and then we have for C and D for square root x, the 24.5 to 25, the 24.9 to 25. You can see our average rate of change answers for our x squared example as well. And make sure you were doing that correctly, plugging into x squared and finding change in y over change in x. So what I'd like to do is now apply these average rate of change calculations to the concept of limits. So looking at this first one, what we're really doing is finding the average rate of change between 2 points where one of the points is getting really close to the other point. We're taking a limit as one of those x values approaches 4 when the other x value is 4, right? So by going from 3.5 to 3.9, we're taking that second x value closer to the other one we're working with, okay? To find the y value of that changing x value, we have to plug into the square root function, which is the square root x part, okay? So the stuff in the blue box can be simplified into this limit, which by looking at your answers, I think we can kind of assume that our y value is getting closer to 0.25. And here's the other example. The limit as x approaches, that's supposed to say 24. I guess we could just fix that really quick right now because we are recording in real time here. This is x approaches 24. Okay, back to the presentation. Of square root x minus square root 25 over x minus 25. And again, we're going to just assume based on what's happening in those two calculations that this limit's getting closer to 0.1. Here is the limit applied to the x squared calculations. The limit as x approaches 3. The limit as x approaches 5. And then based on what's happening in those blue boxes, we're going to make it an estimate of what those limits are approaching. And for the top one, it's 6. And for the bottom one, it is 10. You should be writing all of these down. So go ahead and pause if you haven't already and start and write down these two limits as well as the last two ones that we just went through. And now we're going to apply these to other ones. So if we were to find the average rate of change of x squared from x equals 3 to x equals 4, okay, and then from 3.5 to 4, and then from 3.9 to 4, and 3.99 to 4, that's going to give us some different values, right? But what we're really doing here is taking a limit as x approaches 4. So what you should do is make sure that when you plug in these 3 average rate of change calculations I have on the screen, that the answers are getting progressively closer to 8, We are going to find a way to do these limits quickly and efficiently in Desmos, but for now, make sure that you're understanding why this limit's approaching 8, okay? Pause if you need to before moving on to the next one. Okay, I'm just going to skip right to the limit here. So we're going from 1 to 2, 1.5 to 2, 1.9 to 2, and 1.99 to 2. So what we're doing is we're taking a limit as x approaches 2. We're finding an average rate of change between a point that is getting closer to 2 and then a point that is at 2. So this is how you write that limit. Limit as x approaches 2 of x cubed minus 2 cubed over x minus 2, okay? Because x cubed is our function. If you were to plug in all these average rates of change, you would see that your answers are getting closer to 12. Okay, so local linearity. Important vocab for this next part. Curves look like lines if you zoom in on them enough, okay? And because curves look like lines, we can find what we call this instantaneous slope, which is the slope of a curve at a single point. Okay, so we're able to find that slope due to this concept of local linearity. So really quick, we're gonna pop over to a graph, and I want to show you what this looks like. So this is a parabola. It is curved, but if we zoom in on it enough, it starts to look like a straight line. These 2 points are actually really close together, but we're just so zoomed in, we can see the space between them. If we find the average rate of change between those 2 points, that's gonna tell us the slope of this piece that looks like a line, right? So this is this concept of local linearity. Okay, here's a curve again. If I zoom in on a different point where this is quite clearly curved, it's near the vertex. If we zoom in on it enough, looks like a straight line, right? We can find the slope of that straight line by finding the average rate of change between 2 points that are actually really close together, kind of a part of that same segment that is looking like a straight line. Okay, so that's what we're doing when we're taking these limits, is we're taking these 2 points, making them stupidly close together, and then finding the average rate of change between them, okay? So this is our general formula that you should write down, okay? This is how we find the average rate of change of any function at any x value, okay? C is gonna be a fixed point, and then the second point in our average rate of change calculation is gonna approach C. Okay, example, limit as x approaches 3 of x squared minus 3 squared over x minus 3 is gonna give us the slope of x squared at the point 3, 9. So if we apply this to another example, what is the average rate of change of the function 2x cubed on the interval 1.9 to 2, 1.99 to 2, 1.999 to 2? You can see those calculations off to the right here. What do you think those this limit is going to approach in the y direction? If you're looking at those outputs, what do we think this limit's going to approach? And put your answer here. Okay. So again, we are seeing that this answer seems to be getting closer to 24 as the 2 x values, 2 and 1.9, 1.99, 1.999 get closer together. So how we write this as a limit is we say the limit as x approaches 2 of 2x cubed minus 16. 16 is 2 times 2 cubed over x minus 2. And then we're going to say that's equal to 24. So now we're going to define this as the instantaneous slope of 2x cubed at x equals 2, and we're saying that slope is 24. It is a very steep curve at x equals 2. So you should copy this down again, or if you already have it copied down, that's great, but we're going to label it in different ways. So this first box part is just the average rate of change between 2 points on the graph of 2x cubed. One of those points is 2, 16. The other point is x, 2x cubed. What we're doing is letting those 2 points become really close together, which is going to give us the instantaneous slope at x equals 2. This equal sign is telling us what the slope is, so it is equal to 24. So this curve is a very steep curve at x equals 2 with a slope of 24. Okay, so this is another example. The average rate of change between 2 points on the graph of x squared. One of them is 3, 9, 3, 3 squared. The other is x, x squared. We're going to let those 2 points become really close together by letting x approach 3, and that's going to give us that instantaneous slope at x equals 3. In general, we have 2 points getting close together, and this is going to find us the slope at x equals c, whatever c is. And then it's going to be for the function f of x, whatever f of x is. Okay, so our last example, okay, we want to see how to approach or approximate a limit like this using Desmos, okay? So I'm going to show you how to do that now. The limit as x approaches 2 of 2x cubed minus 16 over x minus 2. So we're going to go back to Desmos now. And we are just going to go, let's reset everything here. So we're going to go f of x equals 2x cubed. That's our function, right? To find the average rate of change of 2x cubed at any x value, we want to use some kind of sliding value. So we're going to do f of a minus f of x over a minus x, okay? Now the x value is going to be our x that's plugged in our example, which is 2, okay? So we're going to change that to 2. And I would recommend you pause and go split screen here so you can follow along with me and know how to do this, all right? We're going to click add slider. And so now what we have is this is giving us the average rate of change between currently 1 and 2. What we want to do is take a limit as that a value approaches 2. So what we can do is just click here and then plug in a number that's really close to 2. And you can see up here that our answer is getting really close to 24. The closer our a value gets to 2, the closer the answer gets to 24. If you go too far, it's going to break because it doesn't, it's, you know, there's a capacity for what this calculator can do. But this is far enough to show that it's going to be 24. So if we want to do another example, let's do this with me now. Let's say we want to do g of x equals x to the 4th, okay? So we're going to do g of a, not f, g of a over a minus, let's say we're going to do it at x equals 5, okay? So what we want to do with our a value now is we want to make it really close to 5. So we're going to make it 4.999, and we can see that it seems like our slope is approaching 500, right? It is a very, very steep function x to the 4th at x equals 5. It's a slope of 500, okay? So you should try to do these two on Desmos now. And this will pause and have you do that and input answers, and then you'll be able to check after you've done them. Okay, so now let's check. We have 5x squared at x equals 4. We have square root x plus 6 at x equals 3. Okay, so we'll go up to Desmos, start over here. So we're going to start with our function. I already forgot what it is. It's 5x squared. Okay, f of x equals 5x squared. So we're going to do f of a over a minus f of, what's our x value? It is 4. So we're going to go f of 4 and then minus 4 here. And then we need to make our a value really close to 4. And what does our limit seem to be approaching? That would be 40. So hopefully you got 40 when you attempted this by yourself. Okay, I'm going to go ahead and change my function now. So we're going to change this to our square root x plus 6. And then I believe we were going to 3, right? So we're going to now let a be really close to 3. We have f of a minus f of 3 over a minus 3. When a gets really close to 3, our limit is approaching 0.16 repeating, which rounds to 0.167. Okay, so yeah, there we go. Hopefully you were able to get that as well. We're going to keep rolling with this. So to really understand calculus, you need to keep accepting that limits are possible, right? You're able to plug in numbers that are extremely close together, basically treating them as the same number. And you want to understand what the limits are representing, which in our context so far, it is just slope, okay? So what you should try to do now is find the instantaneous slope of x squared at 2, 3, 4, 5. And then the instantaneous slope of this is 1/3 x cubed at 2, 3, 4, 5. And you're going to look for a pattern in your answers that you will input in your Google Classroom response, okay? Now, for number 3, don't spend too long on that, but you can try it. You can try to find a pattern for 1/4 x to the 4th and include it in your answer. But I'm more interested in number 1 and number 2 right now, okay? Once you finish that, we will... you will have a worksheet where you will practice applying these limits in a way to calculate slope. And that is what you should work on for the remainder of class and make sure that that gets done before our next class together. Okay, good job, everybody. Thank you.